Okay, so we're looking here at section 1.2 and similar to our first project, 1.2 talks about graphical and numerical limit work. And as we saw, to some extent, when you say graphical and numerical, 1.2 says finding these limits. Well, if you have a well-behaved function and so forth, then finding the limits using a graph or using some sort of tabular thing like a spreadsheet and doing it numerically, those are fine. They work well and so forth. It's the truly ill-behaved sorts of things, or the really strange things, that it can make it very difficult to see an answer that way. But the idea of a limit is relatively intuitive. If for instance, if I visually here, graphically, suppose I draw a curve like that, and I ask, well, for this function, some function f of x, let's say that's 2, and this point here on the curve is 3, then as x moves in this way, or x moves in this way, I can ask, what does f of x get close to? And, well, if you think that's a no-brainer, right, that as x comes in toward 2, then I'm coming along this curve this way, and I seem to be heading for a value of 3. Similarly, if I'm coming in toward 2 this way, and I'm going along that curve, and I seem to be heading for that point, and so the answer appears to be 3. Oh yeah, that's what it is. And we would write this, we would say lim as opposed to limit, and as x approaches 2 of f of x, so we get all this symbology in there. We say we're taking a limit. Well, the limit of what? Well, I guess of f of x, and well, what's happening? We're looking at x approaches 2, and we would look at this picture and we would say, well, it's 3. Yep, it's that simple. Now, though, where limit is kind of weird is limit is a concept of getting closer, and so we're asking what this is heading to, not what it is at 2. And there is a very subtle difference there in many ways. So again, suppose I draw the same sort of thing, but I put a big hole in the graph right there. It's only at that point, but there's 2, there's 3. But now, for whatever reason, the value of my function is 4. So in this case, f of 2 is equal to 4. However, as I come in this way on the x-axis, or as I come in this way on the x-axis toward 2, if I follow along this function curve, I ask, well, what is happening as x approaches 2 on that curve f of x? Well, it's still 3. Okay, so a limit my function doesn't even have to exist there to talk about something like a limit there. So it's in that way it's a little subtle, and all of a sudden here's how math is changing a bit, is that we're asking about a behavior, not a and what something is heading toward, not what it is. All of a sudden, in a way, the answer's not x equals 4 anymore, right? If somebody said, oh, evaluate the function at 2, right? You go, oh, well, that's 4. I mean, it says so right there. But now with this limit, we're actually giving an answer that nothing's there. And so you see, that's a little different. And but in the end, this idea of limit is key to calculus. Okay, and so here we're just sort of without context. We're just introducing this idea of limit. We'll give you some context in a moment. And so this is the graphical. Well, tabularly, what we might see is that if I had my spreadsheet set up and, here's x and here's f of x, and what we might see is if I had 1.9, so, and then 1.99 and 1.999, in my table, as I evaluate f of x, I might see that was, well, from the picture here, it looks like, we'll just go with 2.9, 2.99, who knows, 2.999. Okay, so, perhaps it's looking something like that. And similarly, over on this other side, if I have x and f of x, maybe I was at 3.1 and then 3.01 and then 2.1, 2.01, 2.001, that sort of thing, and maybe this was a value of 3.2, 3.1, 3.05, something like that, as it was heading in there. And so tabularly, I look at this and it appears as this x seems to be going, I'm saying that's getting closer and closer to 2. What happens here? Well, it appears that is getting closer and closer to 3. And similarly here, 2.1, then 2.01, then 2.001. So these are actually decreasing numbers. I could have written them in the other order, and that would be fine. But this also appears to be heading toward 2, and this also appears to be heading toward 3. And so we would say, oh yeah, so the limit as x approaches 2 of f of x is equal to 3, and so we see it tabularly there, and we would just evaluate things and check that out. But like this case up above, it could be that if I actually put 2 into f of x, it wouldn't be defined, and that's fine, that's okay. It's all about what's the behavior in the approach, not what actually happens there. It's all about the build-up, I guess. Okay, so then under sort of what situations doesn't the limit exist? Well, okay. Limit fails. It's like Fail Army on YouTube or something. Limit fails. That's what I could ask you all to do, is come up with Fail Army videos of limits. I don't know. I don't think they'd be very funny, but yeah, who knows. Okay, so one possibility is simply that when we talk about this limit, it has to work unless I say something very specific. From left has to be the same as from right. So in other words, graphically, if I have something like this, and maybe that one's filled in and this one's an open circle, and again, suppose this is 2, then my daughter just came in and scared the living crap out of me. Okay, so that's a 3, and suppose this is a -2, then the problem is if I simply say the limit as x approaches 2 of f of x, well, that does not exist. And the problem is if I come in this direction from the left, I should get one answer. I should get like -2 here. But if I come in from the right like this, I get an answer of 3. Now, so what we can do are one-sided limits. It's okay to say something like, well, the limit as x approaches 2 from the right-hand side, the positive side of 2, so to speak, of f of x, it's okay to say that's 3 because I've put that plus up here on the 2. And similarly, if I were to say the limit as x approaches 2 from the left, or the minus side of f of x, that's equal to -2, and that's fine. But that's one way a limit can fail. Now, another way is simply, so if they don't match from left and right, then the limit as a general limit fails. Now these two one-sided limits exist, but the other doesn't. Excuse me. Then another way limits can be a problem are simply that they don't head toward a number, they're just unbounded. So again, graphically, if I had something like, here's 1 over x squared, x and y. 1 over x squared, if I were to ask, what's the limit as x goes to 0 in this case? Well, this just grows without bound. They're both growing in the same direction, so however close I get on this side and I get on this side, I'm getting kind of that same number, but in this case, again, we would get it does not exist. Now, in this particular case where they're both heading to positive infinity, actually, another way to be a little more specific about the fact it does not exist. So here's what I'll call a math idiom. An idiom is when you say something, but if you took it as literal, it would not be right. It would be untrue. I'm trying to think. I mentioned idiom, and I should be able to come up with one. Well, let's see. I don't know. I'm blanking out. If I come up with one, I'll mention it. But anyway, see, if we take this as literal, this isn't true. I mean, there are problems in a couple of ways. One, we're saying here equals, as if the limit exists, right? You know, we had an equals here when this right-hand limit existed. We had an equals here when the left-hand limit existed. You know, back up here, we had equals when the limit existed. So it looks as if we're saying the limit exists, but it doesn't. It does not exist. This grows without bound. It doesn't head to a particular number. It just keeps getting taller and taller and taller as we get closer to zero. So that's this equal sign is a problem. Okay, that's an idiom, because you know we're saying it equals as if there is a limit, but there is not. And then we write infinity here. So we've got that equals infinity as if infinity were a number. So again, this is another problem. I mean, if we take this literally, we're sort of, it looks like we're treating infinity as a number. And so, and I'll move to a second page here. So what we're saying, limit as, say, x goes to, and I'll just say some a of f of x equals infinity really means as x approaches a from either side, okay, from either side, f of x grows without bound. So I often talk about mathematics as a language, and pretty much any language has idioms in them. Yeah, I just thought, you know, scared the poop out of you. There's an idiom. Right, you know, I mean, it could really happen. I mean, that can actually happen, and that's where that expression comes from. But to generally say that, you know, oh, it scared the crap out of me, or you know, pick your word for feces there, but you know, it scared me that much, right? It didn't really, well, at least not that time, right? It didn't really, you know, so that's an idiom. Literally speaking, it's not what happened, okay? But we all know what it means. Well, so math, it's a language as well, and so it will have idioms, and so this is one idiom. Again, what makes it weird or makes it literally untrue is that we're putting the equal sign for a limit that does not exist, so that doesn't make sense. And then we're treating infinity as if it's a number instead of this concept of growing without bound. And so when we write something like this, or if it was negative infinity, you know, we're saying that actually f of x is simply growing without bound. And if it's a negative infinity, it's growing negatively without bound. Okay, so that's another way it could fail to exist. And now they mention oscillating behavior. What's nice about their oscillating behavior in example 5, you know, so they're showing this again graphically, and they're saying, you know, as something comes in, if it just starts bouncing back and forth so much and so tightly that it doesn't seem to go to any particular number, then again, that limit, you know, does not exist. Well, actually, a slightly better picture in a way that I can see more of what's going on, and this is all the oscillating behavior has to do is, you know, suppose, sure, I've got something that's heading down here towards 0. We'll let that, you know, and maybe this is heading up here towards 0. So it looks like that would be the limit. But every once in a while, there's a little open circle, you know, in here somewhere and there and so forth. And let's just put a dot up here, and then a dot there, and then a dot there. And then have those dots get closer and closer and closer together, right? And so picture, suppose I draw this a little straighter and I say, hey, this is y equals x. Then certainly it looks like as x heads to 0, then so should y, right? Because y is equal to x. And the picture looks that way and so forth. So it looks like that would work. But now suppose I actually do something like make it a piecewise function instead, and I say, well, y is equal to 1 if x equals 1 over n for some integer. So 1, 1/2, 1/4, 1/3, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, 1/9, and so forth. So it's 1 there, but otherwise it's x. Well, if you were to actually graph that and just graph the single points but make them just infinitesimally small, right, you would never notice those dots. But what's happening is, no matter how close I get to 0, all of a sudden I'm going to jump up here to 1. And well, so is it really going to 0? Because I keep jumping up here to 1. And I think if you see that oscillating behavior, it's probably a little more intuitive as to why that's not going to have a limit, because it's, if I'm going back and forth like this, well, where am I? I don't know. I'm between, 1 and -1 or something. I'm not at any particular number. Well, the same thing's happening here, because if I sort of said now, well, connect the dots here as I do it, so it wouldn't be exactly this piecewise function, it'd be some weird function where I come down, I jump up and, connect the dots. Well, that would look like oscillating behavior. And you see they're getting closer and closer together. And am I getting close to 1 or am I getting close to 0 because all the other x's go to 0? Well, I don't know. And, so does not exist, okay? There's the I don't know because it's not well defined. That's an okay I don't know. Like, what's 0 divided by 0? I don't know. It's not well defined. Because then, if the numerator of a fraction is 0, the fraction is 0. Oh, wait, but if the denominator in a fraction is 0, it's undefined. So is it 0 or undefined or something else? Don't know. Right, and that's an okay I don't know, and that just means it's not well defined, and therefore, like in this case, we're saying something does not exist. Okay, so that gets us to kind of the behaviors that cause a problem. Now I'm going to end this video here and then do another one on the formal definition. So we'll stop here.